Assalamu alaikum wa rahmatullahi wa barakatuh. Alhamdulillah wa salatu wassalamu ala rasulillah amma ba'd. So in this lab, we study how to connect a microcontroller with different components, with other microcontrollers or with other components using serial communication. There are three different protocols for serial communication. One of them is known as UART, Universal Synchronous Asynchronous Receiver Transmitter. This is one of them, and later on you'll also study SPI and I2C. So this is one protocol, and there is the second protocol is Serial Port Interface, also known as SPI, and the third protocol known as I2C or I2C, Inter-Integrated Circuit. This is I2C or Inter-Integrated Circuit. So these are the three different protocols normally used for serial communication between two different modules or two different systems or components. The UART protocol, the simplest protocol out of all these three. The main difference between using UART and SPI and I2C is UART is normally used when you are connecting two different systems which are separated from each other, which are entirely different from each other. For example, here you have the remote control in the picture shown here. You have a remote control and you have an aeroplane. So both of these, they are entirely different systems. The remote control has a few buttons for user input, and the remote plane, it simply has a receiver which receives the data from here. So there is a wireless transmission involved, but the protocol which is being used is the serial protocol. And both of them, they are entirely different systems. They are not related to each other. And in I2C, in SPI mode, the SPI protocol is and the I2C protocol, both of these protocols, they are normally used when you want to communicate between different modules on a same PCB. So if you build a PCB, if you build a system, if you design a system on a PCB, and you have different modules connected on that PCB, and you want to communicate, you want the data to be transferred from one module to the other module, then you can use one of these modes, SPI or I2C. So they are normally used when you are communicating between two different modules on the same board or on the same system. Now let's go back to the UART protocol. In this lab, we study how to configure the transmitter and receiver for the UART protocol. So let's start with the data format. So in the UART mode, this diagram or this timing diagram shows you how the data is transmitted. So normally, the transmit pin of the UART module will be normally in the idle state, the transmit pin of the UART module will be high. Whenever you want to transmit a data, it will first transmit a start bit which is a 0. Then you can transmit your data. Then at the end, it will transmit a stop bit. The stop bit is 1. The start bit is 0 and the stop bit is 1. Similarly, in the receiver, it will receive the start bit first, and then it will receive the data, and then it receives the stop bit. So always the start bit is indicated with a 0 and the stop bit is indicated with a 1. This block diagram, it shows you how the transmitter works, how the UART transmitter works. So inside PIC microcontroller, whatever data you want to transmit, we copy that data in this register, TXREG register. This is the name of the register. We copy that data in this register, and then we enable the transmitter. So when the transmitter is enabled, the microcontroller copies this data to the TSR register, transmit shift register. Microcontroller copies the data automatically to TSR register, and it starts shifting the data on this pin, on the transmit pin. So it starts shifting this data right towards the right on this pin. So the data is transmitted on this pin. So as you see in the diagram, the LSB will be transmitted first. So it transmits the start bit, and then immediately after that it will transmit the LSB, then the next bit, until it transmits the MSB at the end. So MSB is transmitted at the end, and then you have the stop bit. Similarly, in the receiver diagram, this is the receive pin of microcontroller. So when the data is received serially on this pin, that received data is shifted inside the microcontroller and copied inside, is shifted inside the RSR register, the receive shift register. So it keeps on shifting inside bit by bit until the whole data is copied, and then once you have this complete data shifted inside, the microcontroller will copy that data to RCREG register. So once the data is copied to RCREG register, the user can copy data from here, or the user can use this data in his own application. The receive shift register is not accessible to the user. The user cannot change anything, or user cannot read the data from this register directly. So user has to wait for this data to be completed. So once the data is completely copied to RCREG register, only then he can use this data. And how can a user know whether the data is completely copied or the data is completely received? That is indicated by the RCIF bit, the flag bit for the receive interrupt. So RCIF bit, it will be set as 1 when the received data is completely copied to the RCREG register. So you have to keep on looking at this bit. When this bit is 1, or you enable interrupts for receiver. So as soon as there is an interrupt, so you have to enable the interrupt for using RCIE bit. So when the data is completely copied, it will generate an interrupt. So you can, inside the interrupt service routine, you can copy the data from RCREG register. Similarly, in the transmitter, the transmit shift register is not accessible to the user. User can only copy data to TXREG register. So once the data is copied to TXREG register, microcontroller will copy it internally. It will copy that same data to TSR register, and it will start shifting to the right. And once the data is shifted completely, TRMT bit becomes 1 after the transmission. So once the transmission is completed, TRMT bit will become 1. So as long as the data is still being transmitted, this bit will be 0. This bit will be 0. TRMT bit will be 0. So before you copy new data to TXREG register, you have to look at this bit. You have to look at the TRMT bit. If the TRMT bit is 0, that means the microcontroller is still transmitting previous data. So you have to wait. We have to wait until this TRMT bit becomes 1. So when it becomes 1, only then you copy new data in TXREG register. Otherwise, it will corrupt, or it will override the previous data. So serial transmission, it needs only one pin for data transmission. So this is the pin, transmit TX pin. TX pin is used for transmission, and in the UART mode, in the UART protocol, you can transmit and you can receive at the same time. So it is a full duplex communication. So you can transmit the data on TX pin, and at the same time, it can also, the microcontroller can also receive some data on the RX pin. So this is a full duplex communication. Now, how fast the data should be transmitted, or how fast the data should be shifted out or shifted in for reception, that depends on the baud rate. Now, baud rate is the same as bit rate, so it indicates how fast the bits are transmitted. So baud rate is measured in bits per second. In the data sheet, you will find there is an equation given. Based on that equation, you have to calculate the baud rate, and you have to load some numbers in this register, is PBRG high byte and PBRG register. So you have to load some numbers based on the calculation to set up the baud rate, or to generate or to calculate the baud rate. And the same baud rate you have to set in the receiver as well. So you'll have a transmitter, you'll have a receiver, and you have to set the same baud rate in both these microcontrollers or in both these systems. So one can be a microcontroller, other can be your own computer, it can be some other module which has serial communication. Now let us look at the registers which are used for data transmission and reception. So these are the registers: TX, STA, and RC STA register. TX STA register is the transmit status and control register. UART module in PIC microcontroller can be used in synchronous mode and asynchronous mode. In our lab, we are only using it in asynchronous mode. So the first bit, the bit number 7 of TX STA register is the clock source select bit. So if you have a synchronous mode, in synchronous mode you can have a master and you can have a slave. So one device can work as a master which generates the clock, and other device can work as a slave device which receives the data and it takes the clock from the master. So in asynchronous mode we are not using this bit, so this bit will be don't care. Then you have TX9 bit. Normally the data that you want to transmit will be an 8-bit data, but sometimes you can transmit 9th bit. So 9th bit can be used either for address detection, or it can also be used for parity check. So here this example it shows you as an address detection bit. So the 8th bit will be the data, and the 9th bit can be used to detect the address for multiple devices that you have connected here. So you have a 9-bit address, and this is the transmitter. You have one transmitter and you have 3 receivers. So if you have an address detect bit enabled, then the microcontroller can decide which device it is communicating with. And the 9th bit can also be used as the parity check bit, as the parity bit. So parity bit is used to detect an error in the transmission. So these are 2 examples for the parity bit. So in this case, in the first case, we have this is the data 1 0 1 0 1 0 1 0. We have even number of ones, 4 ones. So we add a 1 here to make the total number of ones as 5, which is an odd number. So the 9th bit is 1 to make it as an odd number. Here the number of ones is already 3, which is odd, so we add a 0 here. So odd and even parity, depending on that, we either add a 1 or 0 here. So this can detect 1 bit error. So in this case, if in the receiver, if we receive this data, then immediately just by looking at counting the number of ones, we can know that the number of ones here is 4. It's not 5. So it's even, it's not odd. So there was an error in the transmission. The receiver can send a signal to the transmitter, and it can inform the transmitter that there was an error in the transmission, and it can ask the transmitter to retransmit the data once again. So this is the purpose of using this is one application of using 9th bit in the transmission, and the other application is for the address detection as shown here. Now if you want to enable 9-bit transmission, if you want to enable 9-bit transmission, then this bit should be 1. So it selects 9-bit transmission. And where is this 9th bit saved? Because all the registers are only 8-bit registers. So where do you want to, from where do you transmit this 9th bit? The data of this 9th bit, whether 0 or 1, that is here in bit number 0. So data for this 9th bit, the 1 or 0 of 9th bit will be here in this bit number 0 of TXSTA register. Then you have transmit enable bit to enable the transmitter. Then you have synchronous bit, whether you want synchronous mode or asynchronous mode. We are using this in asynchronous mode in the lab. Send B to send synchronous break on the next transmission. And you have BRGH for high baud rate, high speed baud rate. Then you have the TR-empty bit. The TR-empty bit, which indicates whether the transmit shift register is empty or not. So this bit which indicates whether the transmit shift register is empty or not, that is here. That bit is here. So if it is 1, that means it is empty. If it is 0, if it is full and it is still transmitting the previous data. Now in the receive shift register, in the receive status and control register, you have SPEN bit. SPEN bit, serial port enable bit. This bit is used to enable the serial port, whether transmission or reception. Both of them, for both of them, you have to enable this bit or you have to set this bit. Then you have RX9 bit from 9 bit reception. If you want to receive 9th bit, then this bit must be 1. Then you have SREN bit, single receive enable bit. It is not used in asynchronous mode. And you have continuous receive enable bit. So in the asynchronous mode, this bit must be 1. This bit, the continuous receive enable bit must be 1. Then you have address enable bit. So when you are using 9 bit for address, then this bit must be 1. Then these two are the errors, and the 9th bit is indicated here. The 9th bit, the data of the 9th bit will be saved here. These two are the errors: frame error and the overflow error bit. Framing error, it can be updated by reading the RCREG register. So if the start and stop bit, they do not fall within the same frame, within the same timing frame, then this bit becomes 1. And if you want to clear this bit, then you should read the data from RCREG register. Then there is overrun error bit. So to clear this bit, the CREN, the continuous receive enable bit, should be 0 to disable the receiver, and then you can re-enable it again for the next reception. Then you have the baud common register, baud rate control register, and you also have the BRG. So baud rate generator. These are the equations that are used. These are the equations that are used for generating baud rate or for calculating the baud rate. So you have sync bit in TXST register for synchronous and asynchronous mode. You have BRG16, whether you want to use 16-bit baud rate or 8-bit baud rate, and BRGH for high-speed baud rate or low-speed baud rate. So based on the data of these 3 bits, you have to use one of these equations to calculate the baud rate, and this N is the value that you should copy in these 2 registers, SPBRG high byte and SPBRG register. These are all the registers which are associated with the UART module. If you want to use the UART module with interrupt, then from the intcon register you have to set global interrupt enable, peripheral interrupt enable, and from PIE1 register RC enable, receive interrupt enable, transmit interrupt enable. These 2 bits, they indicate RCIF bit and TXIF bit. They are the flag bits for the interrupts for receiver and transmitter, and the priority bits, IP bits. Then you have the RCSTA register, receiver status and control register, TXST register, the TXREG register which has the data for transmission, RCREG register which has the data for reception, the received data, and in the baud con register BRG16 bit. And after calculating the baud rate, the value that you copy or calculate should be copied in these two registers, SPBRG high byte and low byte. Now in the activity, you have to connect two different microcontrollers together using the UART module. So this microcontroller will act as a transmitter. This microcontroller acts as the UART transmitter, and this microcontroller acts as the receiver. Now in the transmitter, you have these buttons connected. So these buttons, you can use these buttons to control the speed and direction of the DC motor. So for example, if this button is pressed, then the motor rotates in the clockwise direction. If you press this button, the motor rotates in anti-clockwise direction. If you press this button, then you increase the speed, and if you press this button, then you decrease the speed, and if you press this button, then you stop the motor. So this microcontroller, which simply transmits some letters to indicate whether it wants to rotate the motor clockwise or anti-clockwise, left or right, or plus or minus. So you can transmit here. It's given here in the template. You can either transmit plus, minus for the top and bottom buttons, the center button S to stop, R for right, and L for left or forward or reverse. Then the receiver, it gets the data of the speed of the motor on timer 1. So it gets the feedback of the motor, and this feedback is once again transmitted back from this microcontroller to this microcontroller, and this microcontroller displays the speed of the motor on the LCD. So the motor is, at the moment the motor is not working, it is stopped. So when you click on this button, the R button, the motor starts rotating to the right. Now I have to increase the duty cycle of the speed of the motor. So as you see, the speed is increasing slowly. If I keep on pressing, it keeps on increasing the speed slowly, and the motor is rotating to the right. And this microcontroller, it receives that data. Now they are connected together. So the transmit pin of this microcontroller is connected to the receive pin of this microcontroller, and the receive pin of this microcontroller is connected to the transmit pin of this microcontroller. This microcontroller is sending the RPM of this motor back to the first microcontroller, and it is displaying here on this LCD screen. And if you want to stop the motor, simply click on this button and it should stop. If you click on this button, it will change the direction. Now as you see, it is rotating to the left now. Okay, so that's all for this lab. Complete the activity and complete the homework given at this link, civil communication modules. So it will explain you the working of UART in detail. It is related to PIC18 microcontroller, but the concept is same. You can apply the same concept for PIC18 microcontroller as well. So complete this homework and complete the activity, and you can submit it online here on Blackboard. وآخر دعوانا الحمد لله رب العالمين سبحان الله وبحمده سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.